dell'orologio con la lei.
ಈ ಹೆಡ್ಫೋನ್ ತೆಗೀರಿಲ್ಲ ನಾನು ಈ ಮೈಕಿಂದ
Artificial intelligence is not just about technology. It is about transforming possibilities into realities. Warm good afternoon to everyone present here. Esteemed guests, respected dignitaries, faculty members, and my dear students. I am Anusha V, Assistant Professor from the Department of AI and BS. And it's my privilege to welcome you all to the inauguration of Ignite AI 2026, organized by Bosco Institute of Technology. Ignite AI 2026 is a week-long initiative dedicated to exploring the transformative potential of artificial intelligence under the theme Exploring Intelligence, Inspiring Innovation and Shaping the Future. To begin this significant day on the graceful note, we will start with a classical performance. I now invite Manasa, a student from 4th semester from Department of AI and BS, to present a classical rendition that sets a dignified tone for today's proceedings. सिद्धिविनायका वरकरिराज वदना वरकरिराज वदना हरनतनय श्री सिद्धिविनायका वरकरिराज वदना वरकरिराज वदना मेरे वेकदंताधरा करुणा भरना मेरे वेकदंताधरा करुणा भरना हरनतनय श्री सिद्धिविनायका वरकरिराज वदना वरकरिराज वदना सकल विघ्नहर गगरे स पप गरे दद पग स सद पग गरे सरे रे सद स सद पद द पग सरे ग पद द स सरे ग पद द स सकल विघ्नहर सगर सरी सद सद पद प द सद पद पग प गरे गरे सरे ग परे ग पद स पद स सकल विघ्नहर सरि ग रे सद सरि ग प पद स द प सरि ग रे ग प द पद स सरि ग रे ग प द पद स स सकल विघ्नहर ग ग रे रे स स द द प प ग ग रे रे स स द द प प सकल विघ्नहर सकल विद्याप्रदा शकुतनि नन्ननु पालिपुदो अकलंक महिमा श्री अकलंक महिमा श्री पुरुषोत्तमना अकलंक महिमा श्री पुरुषोत्तमना भकुता शिरोमणि विख्याता भकुता शिरोमणि विख्याता हरणतनय श्री सिद्धिविनायक वरकरिराजवदना वरकरिराजवदन वरकरिराजवदन वरकरिराजवदना. Thank you. Thank you, Manasa, for that wonderful performance. To symbolize knowledge, purity, and the beginning of an enlightening day, we will now proceed with the lighting of the lamp. I will respectfully invite our dignitaries to kindly come forward for the ceremonial lamp lighting.
We are going live in YouTube. Make silence. Silence. We are going live.
And one announcement is that we are going live in our YouTube. You can share the link to your friends and our group, add it up in our status.
मार्केट क्या शिप तेरा बाजार दोपहर को बंद नहीं होता है और नहीं भी है?
Thank you everyone for gracing this moment with your valid presence. Before we proceed further, it is my honor to acknowledge and welcome the distinguished dignitaries. At the very outset, let us remember with the reverence of our beloved founder, late Shri B. Bailappa, President, Vayanamak Education Trust. His vision and dedication continue to inspire and guide this institution. We also extend a warm welcome to Shri B. Manjunath, Executive Director, DBIT, in his absentia for his constant support and encouragement. We also respectfully acknowledge and welcome Shri Raghav Bailappa, Secretary, DBIT, in his absentia, whose leadership has always been source of strength for this institution. At this moment, I would like to extend my heartfelt welcome to our esteemed guest, Dr. H.D. Ananda, former Group Director, SPROC System, Master Control Facility, ISRO. I request our principal to kindly welcome our esteemed guest with a sampling as a token of appreciation. I also welcome our respected principal, Dr. Nagabhushana B.S., whose leadership constantly inspires the academic excellence of our institution. Also welcome our Dean Academics, Dr. Guru Prasad M., for his continuous support in driving the academic growth and innovation. And also welcome our Dean R&D, Dr. Nataraj K.R., for his continuous support. I welcome Dr. Gauramma G.S. and Dr. Shashidhara H.R., whose commitment to student success strengthens the foundation of our program. I also welcome all the heads of the department, faculty members, non-teaching staffs, and my dear students who are the backbone of every successful academic initiative. We are deeply honored to have each one of you here today. To share a brief overview and vision behind the exciting initiative, I now invite Dr. Gauramma G.S. to enlighten all of us about Ignite AI 2026. Good afternoon, everyone. It is my great pleasure to welcome you all to the Ignite AI 2026, a week-long academic and innovation event organized at Bosco Institute of Technology. AI is rapidly transforming the world around us, from healthcare and education to finance and smart cities. AI is becoming a powerful technology that is shaping the future. As engineering students, it is important for you to understand not only how AI works, but also how it can be applied to solve real-world problems. With the vision, Ignite AI 2026 has been designed to create awareness, enhance technological knowledge, and inspire innovation among students from different departments. The event brings together a variety of engaging activities that encourage learning, collaboration, and creativity. Throughout this week, we will participate in several exciting sessions, including technical talks, workshop, ideathons, quiz, debate, poster presentation, and project exhibitions. Each day focus on a unique theme. We begin with AI Vision Day, which introduces the journey into AI. This will be followed by a session on AI-based content creation, statistical literacy in AI ML, and ideathon, prompt engineering, natural language processing workshop. You will also have opportunity to participate in AI Project Expo and interactive activities such as debate and quizzes based on AI. The event will conclude with a panel discussion with alumni, academicians, and industry professionals, where they will share insight about AI revolution, its opportunities, challenges, and future innovations. Dear students, this event is not just about learning technology, it is about thinking, creativity, collaborating with others, with other departments, and exploring how AI can be used to build innovative solutions for society. I encourage each one of you to actively participate in all the activity, ask questions, share your ideas, make the most of this learning opportunity. Let this week ignite your curiosity, expand your knowledge, and inspire you to become the next generation of innovators in artificial intelligence. Thank you, and I wish you all a very successful Ignite AI 2026. Thank you, ma'am, for giving us a clear insight into the vision and purpose of this event. It's now my privilege to invite our respected principal, Dr. Nagabhushana B.S., to deliver the welcome address and share his thought with us on this special occasion.
Dignitaries on the dais, respected faculty, and my dear students. As indicated by Professor Gaurama, it's a matter of great privilege and also a matter of pride to conduct this Ignite AI 2026 on our campus. I take this opportunity to respectfully recognize the support given by our senior management in conducting this event on our campus. Equally grateful am I on behalf of every one of you to extend our heartfelt thanks to Professor Gaurama and also Professor Shashidhar, who have relentlessly worked towards realizing this momentous occasion we are passing through today, and which is going to be live for 1 week on this campus. As indicated again by Professor, AI is something which is a technology which is something growing at Renaissance speed on a global scale. So it is important that as institution, so it is our responsibility to really have an ambience of AI on this campus so that our students are in a position to pick up the technologies just in time and be industry ready to face the challenges. So given that, there is always a question which keeps bothering every one of us. And also, even outside in the employment scenario, is AI going to really snatch away the jobs of our technical folks? So my personal opinion in that is, it is only that the type of job that people are going to be doing is going to change. And such type of changes we have always adapted from the past 3 to 4 decades. For example, if you take the software development, maybe 2000 minus, it was totally different. And over a period of time, we have seen a lot of changes, and we all have got adapted to the newer technology. As such, in my personal opinion, it is yet another layer of technology which is going to reinforce on the existing plethora of technologies, bringing in a lot more comfort to human life, making this world a better place to live. And the flip side on this thinking is that it is very important for us to really note what are we losing by these AI innovations. So finally, it will touch upon some of the factors which we don't even have any glimpse of. For example, so it's really going to create some level of confusion which is really hard to define at this point in time. Specifically, one of the greatest sort of flip side to this burgeoning speed with which the technology is growing is in terms of energy sector. So every computer is going to become a big guzzler in terms of energy, and there are going to be a lot more data centers which are going to be in existence in a lot of places on a global scale. And the type of energy that it is going to consume is going to be phenomenal. And should it really go beyond certain level, it is going to be detrimental to our life. That is one important flip side. The second flip side is in terms of the application areas. So we may have to really deploy the applications based on AI technology, which is going to be the futuristic type of job which our students are going to be going to be responsible. So the flip side here is that in terms of the security, so as we make an entry into all walks of our life, there is a very chance that security is going to be at stake to a large extent. So having said that, so these two and many other flip side to the growth of these technologies. So what is important for us is to be really, be aware of such of these things and then deploy the necessary, innovations in this technology in a judicious manner aspects. So we don't have to be really worried about that as long as we are mentally prepared to really face the change and adapt to such changes. In this particular context, I would like to respectfully recall Professor Ananda, who is with us, who is, in my opinion, sort of, the encyclopedia with respect to space science. And having spent around 3 to 4 decades in this, in ISR world, so he's, needless to say, has become a stalwart and an expert in space science. But in addition to that, what I recognize in him is what our students really need to carry, the passion to learn. So that's what I have noticed. I am in touch with Dr. Ananda for quite some time. Every time I have noticed that Ananda comes with a lot of inquisitiveness and passion to learn, even at the senior level he is presently in. So that is something which not only the students, we as faculty also should carry. Having said that, I won't take much time. I am sure we have a lot of things to learn from Professor Anand, and I leave the stage, and before I leave the stage to Dr. Anand, I once again respectfully welcome to our campus, and also I would like to express my sincere thanks to the organizers of this event for giving me an opportunity to speak a few words. And lastly, addressing the students, as Professor Gaurama made it clear, it is important that you students spend your time usefully and then learn the technologies, and through the sessions that we have organized this week long, every day afternoon, and see to it that you develop some seed value during this 1 week, which you probably would nurture, and I'm sure we as teachers are always with you to really see to it that your dreams and your anxiety in terms of the speed with which this technology is growing, so we try to support you to the best extent possible. That being the case, I would sincerely urge that students have to take, because it is after all for the students this event is organized, I request and I submit and I urge that students need to take these week-long sessions so carefully and also with a lot of interest and passion, so that you are good in making your future career prospects bright. Thank you so much.
Thank you, sir, for your inspiring words and encouragement. To formally introduce our esteemed guest and provide us with an insight into their remarkable professional journey, I now invite Professor Anu R., Assistant Professor, Department of Physics, to present a profile of our esteemed guest. Good afternoon, everyone. I am Anu R., Assistant Professor, Department of Physics, and it's my great privilege to introduce our esteemed guest, Shri H.D. Anand sir. He completed his BSc in PCM from University of Mysore in 1984 and his MSc in Physics with specialization in solid-state physics from Mangalore University in 1986. He also obtained a postgraduate diploma in computer programming from University of Mysore after studying at Malad College of Engineering, Hassan. He began his professional career as a lecturer in physics at Malnad College of Engineering and later worked briefly as a PhD student at the Indian Institute of Science. In 1986, he joined the Indian Space Research Organization at the Master Control Facility, Hassan, where he served with a great distinction for several decades. During his long and remarkable career at ISRO, he worked in a spacecraft operation, satellite control, and mission critical software system. He served as a spacecraft control and shift manager, managing the round-clock operation of geostationary satellites and analyzing spacecraft telemetry data. He was also deputed to Fiumicino, Italy to support the INSAT 2D mission and orbit rising operation as an ISRO representative. He held several important positions in the computer system and simulation groups and played a key role in development, testing, evaluation of software systems used for a spacecraft operation. He also contributed to the implementation of IEEE 12207 software standards within ISRO and served as a member of ISRO Software Control Board. Later, he worked in the success is not just about achievements, but about inspiring others to achieve. Now, on behalf of DBIT, I extend a warm welcome to our respected guest, Dr. H.T. Anand, sir. Thank you. Thank you, ma'am, for the clear and articulated introduction. As a token of our gratitude and appreciation, we would now like to facilitate our esteemed guest. I request our principal and I kindly come forward for the felicitation ceremony. Thank you, everyone. Thank you, sir. Before we hand over the mic to our esteemed guest, I would like to invite Professor Shashidhara HR to deliver a vote of thanks.
So very good afternoon, one and all. Respected Chief Guest, Dr. Ananda sir, dignitaries, faculties and students. I am grateful to propose vote of thanks for today's inaugural ceremony of Ignite AA 2026. Dr. Ananda sir, your insights and guidance have truly set the tone for our students on this event. We are honored to have you share your expertise with us. To our management, principal sir, deans, HODs, thank you for your support and encouragement. To our students, let's leverage this platform to explore, innovate and shine. Thank you, Anandal, to make this Ignite AA 2026 memorable start. Thank you, Anandal.
Thank you, sir. It's now my honor to invite our esteemed guest, Dr. H.D. Ananda, former Group Director, SPROC System, Master Control Facility, ISRO, to address the gathering and share his valuable insight with us. Over to you, sir.
ಅವ್ರ ಪೆನ್ ಡ್ರೈವ್ ತೊಗೊಂಡ್ರೆ
Hello? Hello? Fine. First, let me sincerely thank the college management, the principal, for inviting me to this esteemed organization and share knowledge with students. And I sincerely thank Kausalya Madam, who has been in touch with me. Last year also I had come to give a talk on a different topic. So I sincerely thank the management this. Sir, ನನಗೆ ಎಷ್ಟೊತ್ತನಕ ಟೈಮ್ ಇದೆ? I have how much total time? How much I have? 2 hours. Okay. Now, since this is a very new area, in order to take you from the conventional way of computing to the quantum computing, I need some time. I have to change your perceptions first. So to change your perceptions, now whatever material you have in this, you need 3 hours. That much material is there, including quantum communication. I am not talking for 3 hours. I am talking for minimal things what is required for you for quantum computing. Some basics we will bring in because you should have different session with a break. So we will have some 45 minutes to 50 minutes maximum. So that which are the prerequisites, unless you know you cannot understand. So that we will bring in. And after that, since it is an AI week, I have a separate module done, quantum computing application in AI, ML and DL. Okay, that we have some 15 to 20 minutes, 15 minutes may be required. I have prepared a small module. Wherever I go, people may think, why you should go for quantum computers? Whether quantum computers are realistic in nature, whether you are going to get a quantum computer like a desktop what I have today, what is the realistic time frame? So I prepared a module with my ingenuity, few slides to give an insight that when you are likely to get a quantum computer and a desktop. So probably 45 to 50 minutes for the basics what I wanted to tell. Even though material is there for 3 hours, I will just to cut short by looking at my time, and another 15 minutes for your AI and ML application briefly to give you, because it's no week. And after that I need another 10 minutes to tell why we should go for quantum computer. At the end I want to show you a video, what I am talking. You should not feel that it is not a science fantasy. It is real. That is the way fundamental particles behave at the quantum level. I want you to make you to understand. So I want to show a video for 15 minutes, which is quite interesting. Okay. With this, probably everybody, when you look at look at computers, the first thing comes to your mind that a computer will have a screen, a keyboard, a processor, and so many etc. other electronics. That is a perception. It could be a desktop or a laptop. That is the mindset which comes to you. Okay. But now onwards, please change your perception that whatever I am talking is not the physical hardware what you are looking for. Here you are not getting a screen, a keyboard, a mouse, a processor. Of course, quantum computers are there. I will show you at least one image of one of the companies. In fact, the material contains what are the latest advances done by different IT companies in the world, IBM, Google, Microsoft, Rigetti, and AWS, Amazon, and there what kind of quantum processor that they have, what kind of technology, a lot of information is there. I have updated my email looking at the latest processor available, what is the physics behind that. So that's why I said it is 3 hours module, because I have continuously updated the module. So you have to change your perception of looking at computer being have a laptop and a keyboard. You think that you are going inside an atom. Okay? You change your perception of computing as a laptop with a keyboard, mouse, and a processor. You assume that you are going to a film and going inside an atom. and you feel that you are an electron revolving around the nucleus. Okay, a fundamental particle. Now you are a fundamental particle. I use your fundamental physical properties of an electron or any other quantum system photon or an atom, etc., etc. I use their physical properties to store, retrieve, transmit information, make decisions, calculations. That is quantum computing. Got my point? So your perception, of course, you need a hardware to generate these quantum systems. What I am going to talk, a special hardware is there that is quite complex. I will show you. You will be surprised. It needs investment of millions of dollars. So you have to change your perception of going a conventional way of computers, going inside an atom. You look at the fundamental particle, all quantum systems, use their physical properties to store, retrieve, transmit information and make decisions. That is quantum computing. Okay. Now, next. Gordon Moore, who is the co-founder of the Intel Corporation, had predicted what is called the Moore's law. What he said, as the miniaturization of chips goes on, you go on reducing the chips, there is a saturation. Beyond that you cannot miniaturize these chips. So now probably in the mobile laptops or the chips has gone to a nano level chips. Now one interesting thing, what happens is, when you go on reducing the size of a material up to 10 to the power of minus 9, all the physical laws which are valid will work. The moment you bring down an object size or a material size below the 10 to the power of minus 9 level, which is a nano level, all the physical laws are no longer valid. The physical properties will entirely change. Very interesting and astonishing properties starts coming. So that's why you have got one limit called nano scale. That's why you got nanoscience and nanotechnology. So 10 to the power of 9 is one cutoff limit where the physical laws which are valid, which are conventional classical laws, are valid. Beyond 10 to the power of minus 9, classical physical laws are not valid. The particles behave in quantum mechanically. You have to apply quantum mechanics. So now the expected growth of electronics, people started to, because see, for anything when you cannot miniaturize beyond 10 to the power of 9, there is no. So even though if you increase, your computing power will not increase. So people started looking at alternative computing paradigms, whether I can achieve speed up in computing. Next. So extremely small sized devices have been developed and have been miniaturized. And at small sizes, the laws of fundamental laws of physics are no longer valid, which I told the classical limit of 10 to the power of minus 9. So now, quantum computing is one of the promising paradigms people thought which will provide a speed up of conventional computing. So quantum computing provides a theoretical framework taking the laws of quantum mechanics to its advantage. Okay. Next. Now, in the case of classical computing, for example, in the case of conventional computers, you type certain information, finally they are translated into zeros and ones. Okay, for a given input, you are able to predict the output. Means that the results are deterministic in nature. Okay? In the conventional computers, for a given set of bit string, you apply certain logic gates to do operation and get the output. So the output is predictable. Fine. Now what I do, I take a coin. One coin ತಗೋತೀನಿ, ಟಾಸ್ ಹಾಕ್ತೀನಿ. ಅದು ನೆಲಕ್ಕೆ ಬೀಳೋವರೆಗೂ ನನಗೆ ಗೊತ್ತಿರಲ್ಲ. I do not know whether you are going to get a head or a tail. when single coin is tossed, the probability of getting head is 50%. The probability of getting tail is also 50%. Okay. So quantum computing is probabilistic in nature. In other words, quantum computing, so basically quantum computing manipulates the information using the principles of quantum mechanics. The results are probabilistic, like a tossing of a coin. So now what I will do, I have taken one coin and tossed up. At the periodic bureau actually you have got two combinations only. One coin, two coins I will toss up simultaneously. 4 combination, 4 combinations ಇದೆ, 2 squared. ಕೆಳಗೆ ಬೀಳೋವರೆಗೂ you do not know which combination you are going to get. Similar to the tossing of a coin analogy, the electrons are revolving around the nucleus in different orbitals or energy levels with a velocity equivalent to the velocity of light, such as speed. At any instant of time, as long as the electron is revolving directly, it can be there in any of the levels, similar to the tossing of a coin. Till the coin falls down, no, you will not come to know head you are going to get or tail you are going to get. Now, the electrons are revolving around the sun, a single electron revolving. Assume that like tossing of 2 coins, I said 2 coins I have tossed, there are 4 possibilities, 4 combinations you get. When it falls down, you get only one measurement. Similarly, electrons are revolving around the nucleus, 2 electrons say are revolving around the nucleus with a velocity equivalent to velocity of light. Till I make a measurement that whether those 2 electrons are there in the lower energy level or the next energy level, these 2 electrons can be there in all the possible energy levels simultaneously. You got my point? Like similar to the tossing of a coin. But once I make a measurement, depending on the number of electrons which, okay, I get the electron will get collapsed to one of the energy levels. Suppose if it is there in the first energy level, it may collapse to the lowest energy level, next energy level. If the second electron is there in the third energy level, it may get collapsed to the second energy level. Now what I do, the electron which is very near to the nucleus, the lowest energy level, electron is like a bar magnet, simple bar magnet. So electron has got a property what is called the spin. It has got an up spin when it's there in the lower energy state. When it gets excited, it goes to the end, it changes its spin. It will have, the spin direction changes. Now, I use this property of spin direction or the transition of electron from lower energy level to high energy level to store and retrieve information. Got my point? So, the other words, the electron which is very near to the lowest energy level, I represent it as 0 as downspin. I impinge a photon of light, the electron will absorb energy, gets excited, goes to next energy level, spin direction changes. It goes, the spin direction changes to downspin to upspin. So I represent the spin direction as 1. I have told about one electron. Now suppose I have got a group of electrons, an ensemble of electrons. Before I make measurement, I can have initialize the system with so many electrons having upspin, downspin simultaneously across so many energy levels. The beauty of this is, if I make a measurement, electrons can be there in all the energy levels simultaneously. Once I make a measurement, I get one measurement, which will collapse to one of the levels. Means that, like similar to the tossing of multiple coins before it falls down, you have computing power exponentially increasing. Suppose if you have got 3 electrons, before I make a measurement whether these 3 electrons are having upspin or downspin, 2 cubed, there are 8 combinations. your computing power is 8 times faster than your classical computer, where you can get, for a given input you can get one output. Whereas here, till I make a measurement to find out whether the electrons are having upspin or downspin, the 3 electrons can be distributed across multiple levels simultaneously. So all these 8 combinations will get altered simultaneously once you make a measurement. That's why you have a massive parallel computing power processing coming into the picture. So as your number of qubits increase, your computing power also will increase exponentially. Suppose you have n qubits, 2 to the power of n will be your computing power. You have so many number of combinations, and finally you get one combination of that. So that is why computing power with respect to representing information as a spin direction to store and retrieve information, you have a massive parallel processing picture, and here it is results are probabilistic. That you should understand. Next. Yeah. So now ನಾವು ಮಾಡ್ತಾನೆ ಹೇಳ್ತಾರೆ ನನಗೆ ಇನ್ನೂ ಸ್ವಲ್ಪ ಮಧ್ಯದಲ್ಲಿ ಎಕ್ಸ್ಪ್ಲನೇಷನ್ ಇದು ನಾನು ಹಿಂದೆ ಮುಂದೆ ಅವ್ರು ಹೇಳ್ತೀನಿ ನಾನು ಮಾಡ್ತೀನಿ ತೊಂದರೆ ಇಲ್ಲ. ಸಿ ನಾವು ದಿ ಕ್ವಾಂಟಮ್ ಇನ್ಫಾರ್ಮೇಷನ್ ನೌ ವಾಟ್ ಐ ಸೆಡ್, if you consider a single electron, we call it as a qubit. An isolated single electron, we call it as a qubit, which can be in possible states 0 and 1 means lower energy and higher energy level simultaneously. Once I make a measurement to find out whether electron is there in the lower energy level or a energy level, I get one of them. But till I make a measurement, it can be there in both lower and high energy level simultaneously, which is we call it as superposition. Please understand the word concept, superposition, where a quantum system can be there in multiple levels simultaneously till I make a measurement. Once I make a measurement, it collapses to one of the base levels or the energy levels, and you cannot recreate it, you cannot use it. Once you make a measurement, it is valid, that's all. We call it as D squared. So measurement is only once. Fine. And now, the possible states that I will explain, that few basics I will just tell. That is what is called Dirac notation, what I have written. Now in the conventional way, they represent the information as zeros and ones. We use conventional logic gates, OR gate, NAND gate, or any combination of gates to translate and change the bit to flip and get some output, exclusive OR gate, whatever it may be. You do all logic gates and get the information. So in this case, flipping of a qubit is nothing but changing the spin direction of the electron from downspin to upspin. That's all you have to do. How do you do? There are different ways. So you may be getting an idea of, I have told only one property. There are few more properties coming into the picture. I have told about one quantum system. So now, for example, to make it easy to understand what a quantum system is, I have these two sirs, quantum system 1, quantum system 2, looking at me, sir, you are looking at me. Now this is, when you are looking at me, I call it as 0, 0. Now you ask this sir to change this there, akade tirkolake heltini. Tirkobedi. Tirkondre, ivaru 0, ivaru 1. Next, ivaru tirgake heltini. 1, 1 agutte. Innobru add madidre, iದೇ ತರ, each of them is a quantum state. So with 2, I have got 4 combinations. When I increase the third person, you get 8 combination. When I get 4th one, I get 16 combination. When I make a measurement, I am getting only 1 combination. What is called a quantum state? Again example, ನನ್ನ ಕಡೆ ನೋಡೋ ಹಂಗೆ ಮಾಡಿ ಒಬ್ಬರನ್ನು ತಿರುಗಿಸಿದ್ರೆ second combination you will get, ಇಬ್ಬರು ಕಡೆ ತಿರುಗಿಸಿದ್ರೆ third combination ಸಿಗುತ್ತೆ. So this is the way to understand a quantum system. So basically, what is required is, you need a hardware to generate a quantum system is an ensemble of group of electrons, and initially I set up these electrons having upspins and downspins. I use certain quantum gates to change that direction. I write an algorithm or a quantum circuit to solve a problem. So finally a quantum computer will have a hardware which will generate these quantum systems, a group of electrons. That's why I call it as, normally you would have seen the quantum processor, 105 qubits. 105 qubits, when I say, it is generating 105 electrons simultaneously, which can be manipulated and controlled by an external laser source or a microwave source. This is one problem. The second thing is, you know photons, light. Okay? Light is having dual nature. It is both having particle nature, it has got a wave nature. Now, probably in PUC level, you have heard about what is called polarization. Okay? Polarization. You have a left-hand polarization, right-hand polarization, circular polarization. You have a polarization direction. Now, this polarization direction is also another physical parameter to store, retrieve and manipulate information. Fine? So I can prepare a photon having both LHCP and RHCP simultaneously using a specialized nonlinear crystal. I can split it. I can manipulate the polarization state. So second property what I use, one is the spin direction, second one is the polarization state. Next. Yeah. See, once I already told you, once you measure a mega emit, the qubits, the electron will get collapsed to the lower state. Next. Once again, a qubit can be an atom or a photon or an electric circuit or any other quantum system. Okay, we'll just come back. Next. This is what I told. Whatever I told till now, the lowest most electron, lowest most energy level, we call it as orbitals, energy levels. So innermost I call it as 0. Next high energy level as 1. Next. Yeah. Next. I have given 2 electrons. 2 electrons I have told. It can be there till I make a measurement, 2 electrons are revolving in 4. So you have got 2 square 4 combinations. When I make a measurement, I get only 1. So this is the superposition what I was trying to explain. Next. Yeah. So now, see, normally, understand you should have a good knowledge of linear algebra. Unless you are familiar with linear algebra, with vector spaces, eigenvalues, matrices, tensor products, it is difficult to understand quantum mechanics. But when you write the code, you don't need this mathematics. But problem is when you are writing a code, a Python code, which you quantum gate to apply, you should know mathematics. Because directly you will have libraries, you will give a call Harvard gate, it will give a call. But which gate to apply, you should know the knowledge, the mathematics you should know. Okay. So basically, this is a state vector where 2 qubits, where ABCD are the complex numbers. The beauty is the actual information is stored in these coefficients. Actual information is stored in that coefficients. Okay? So once you apply a gate, a quantum gate to change the state of a qubit, all the states will get changed simultaneously, you get one combination. Whereas in classical computers like here, no, when you give 1 0, you get one of the combination based on that. But here, all the combinations what I told, like 2 to the power of 3, no, all will get changed simultaneously. That is why you have massive parallel processing. Now, in other words, qubits are made up of controlled particles, means that you need a hardware, a specialized hardware to generate a set of electrons or a set of atoms or a set of ions or a set of photons. Photons manipulate through an external hardware using a laser source or a microwave source with a nice controlled electronics and a readout method. Okay? And you need devices, for example, ions can be trapped using magnetic field. Ion will have an upspin and a downspin. So ion also can be manipulated. So ions, cold atoms where you have a dispersion of atoms. Okay, there are different technologies. So I am just telling about that. So finally, now you may be getting an idea of what a quantum computer looks like. A quantum computer have an hardware where you generate these qubit systems, the control particles, and the means to control, and by an external source. How do we do? There are different ways. Okay, fine. Next. Yeah, I just only 1 or 2 slides about you should know this much only, quantum mechanics. See, basically, in physics, whatever theory you propose, you should prove, either qualitatively or quantitatively. If you have a mathematical proof, it is quantitative. If you don't have a mathematical proof, it is qualitative. Okay. Quantum mechanics actually gives a mathematical framework for proving physical theories. Fine? Now, the quantum state spaces, whatever I explained, the upspin and downspin, suppose the electron going from lower energy level to higher energy level, in between if it is there, ಹೋಗ್ತಾ ಇದೆ ಮೇಲಕ್ಕೆ, 0 ಇದ್ರೆ ಅದು ಪ್ಯೂರ್ ಸ್ಟೇಟ್ ಏನೇ, ಹೈಯರ್ ರೇಂಜಲ್ಲಿ 1 ಅಲ್ಲಿ ಇದ್ರೂ ಪ್ಯೂರ್ ಸ್ಟೇಟ್, ಲೈಕ್ ದೃಶ್ಯಂಕು ತರ ಮಧ್ಯದಲ್ಲಿದ್ರೆ is an impure state. Okay, so now all these representation can be represented using matrices and vector spaces. There is a special notation what is called a bracket. This much only you know, that is enough. What is called a bracket notation. The first one is called the phi, which is a column vector which is used to represent the quantum state, like whatever I was telling, the upspin or the downspin. Bra is what is called the conjugate transpose of that. That much is enough for you. Next. See the notation of phi 1 and phi 2, which is the inner product, to represent the product of 2 quantum state. Okay, this is now what is important is, in order to locate an electron around the nucleus at any instant of time, I need a mathematical function. Okay, in order to locate an electron, where it is there, at what time frame it is there, which position it is rotating, with what speed it is rotating, I need a mathematical function. That mathematical function is what is called the wave function. Wave function is a mathematical function which gives the position and time variable of a quantum system at any instant of time. It contains all the information related to a quantum system, like electron going around the nucleus at any instant. So I represent it by means of what is called the wave function. That much is enough, you don't worry about that. So wave function is a mathematical function which gives the position of a quantum system at any instant of time in time variables. Okay, that is the easiest way. Now the wave function phi I can represent using a constant alpha, which I told it as a constant, upspin plus beta downspin, and I am information I am storing in these coefficients. What I am going to change is only these coefficients, not the spin direction, not the base states. Okay, next. So such an observation is called a measurement. The spin up is called 1, the spin down is called 0. Okay, now as I told, instead of 1 electron, if I have got a group of electron, 10 electron, 20 electron, depending on which atom you are using, I can have an ensemble of electrons, a group of electrons. Before I make a measurement, I can set a system, I can have a quantum chip which will generate a group of electrons having upspin, downspin simultaneously. Suppose there are 105 electrons, I have 105 electrons simultaneously. The computing power is 2 to the power of 105. I initially set up having some of them having upspin, downspin. By external source, I can manipulate the spin state. Depending on my problem, how many qubits at a time I want to manipulate, I can manipulate that spin direction using an external hardware. Okay, so an ensemble of electrons can this in a 4 position. So measurement of an ensemble means group of electrons collapses to one of the combination which is called the kth state. Now the problem is, if you consider only one electron out of so many, like sir Shashidhar sir ಕೂತಿದ್ದಾರೆ, isolate ಆಗಿ ಕೂತಿದ್ದಾರೆ, he is a qubit now. ಮೇಡಮ್ಗಳು 3 ಜನ ಇದ್ದಾರೆ, is an ensemble of electrons, group. See, quantum state of an individual electron is called a qubit. When you have got group of electron or an ensemble, that is the difference between a qubit and any symbol of electrons. Fine, next. Now this is what I was telling, the spin direction. So spin direction normally you cannot measure. There are ways to measure the spin direction where we change the charge conversion. The spin is converted into charge, whether it has a positive charge or a negative charge, we find out the measurement. Okay? So this is the way I to represent qubits representation. Next. So these are this many areas of mathematics you should have the knowledge. I am not going to explain. You should know about vectors and vector spaces, inner and outer products, quantum states, quantum gates, eigenvalues, tensor products and unitary matrices. This much knowledge you should have to understand quantum computing and implement your quantum algorithm or write the code. This much knowledge you should have, you should get at least expertise. Next. Yeah, so there are different ways, I don't want to explain, just note down. You have got a wave function already I have told you. Next. Next. You have got a state vector already I told you, that is phi is equal to alpha into upspin and beta into, that is the state. You have density matrices I told, no, like Trishanku, like electron is going from lower energy to higher energy level, it is in between, ardhadalli there. It has absorbed energy, it is still not reached the higher energy level. To represent, it's an impure state. How to represent the impure state? Using density matrices. Next. A pure state already I told, 0 or 1. Okay? Next, we got a mixed state. That is some you have like Trishanku Tara. Next. An entangled state I will come back. Coherent state also will come back in next slides. Next. Ideal state. Okay. Next. Munduk hogi. Next. Yeah. Quantum registers idella beda. Next hogi. Yeah. One more thing I want to tell. Now, this quantum information, what is the spin direction, what I told, no? Whatever spin direction or the polarization state, it is very, very, very delicate. The information or what is called a quantum information, whatever we are going to store in the memory, I have to store the spin direction, I have to store the polarization state. This information what I am going to store in a memory, what is called a quantum memory, it's very, very delicate. ಈಗ ನೀವು ಮಾತಾಡ್ತಿದ್ದಾಗ ಪಕ್ಕದವ್ರು ಯಾರು ಡಿಸ್ಟ್ರಾಕ್ಟ್ ಮಾಡ್ಬೋದು. ಇನ್ನು ಫೋನ್ ಕಾಲ್ ಬಂದು ವಿಲ್ ಗೆಟ್ ಡಿಸ್ಟ್ರಾಕ್ಟೆಡ್ ಇಮಿಡಿಯೇಟ್ಲಿ. ಆಯ್ತಾ? ಅಕಸ್ಮಾತ್ ಸೆಕೆ ಆದರೆ ಬೆವರು ಒರೆಸ್ಕೊಳ್ಳೋಕೆ ಐ ವಿಲ್ ಗೆಟ್ ಡಿಸ್ಟ್ರಾಕ್ಟೆಡ್. Similarly, this quantum state is so delicate because of the noise generated by the surroundings, maybe the thermal circuits, temperature ಜಾಸ್ತಿ ಆದ್ರೆ the quantum information will get disturbed. It's very delicate. And any done on the disturbed system will not give useful results. We call it as decoherence, means that quantum information is very, very delicate, it is error prone. See, ಏನಾಗುತ್ತೆ, for example, ಈ instant of time ಅಲ್ಲಿ I will find out, some means I will give a query, I will find out this electron is having upspin. Upspin I will come to know. Till I make the second measurement, thermal noise in the upspin, in the downspin, automatic change ಆಗೋಯ್ತು ಅಂತ ಇಟ್ಕೊಳ್ಳಿ, because of some reason, because of the error. Now I should be able to detect that there is an unwanted spin direction change. I should correct it also. So error detection and correction is a challenge here. So holding the quantum information for a long time and maintaining its integrity is a challenge. That's why all companies are spending millions of dollars in looking at the error correction codes. Why scaling up of qubits is difficult? Because as the number of qubits you increase, the error rates will increase. The unwanted spin direction change will increase. And you should detect that unwanted spin direction change and correct it. Okay, suppose if I make, before I make a next measurement, I should detect and correct. If I don't do, you will get a wrong result. That's why quantum information is very delicate and prone for errors. So error correction and detection one has to do carefully. Okay, next. Yeah. Now problem is, I talked about what is called qubits. Qubits are actually the real physical entities which are generated through a quantum hardware. I already told you, this quantum hardware is whatever qubits which are generated for error prone. It will get disturbed by environment. But when you write codes or when you write quantum algorithms, you want the information, the integrity of the information to be stored. Okay, means that even if there is a noise, 10 ಜನ ಪಾತಿರ್ಬೇಕು, 4 ಜನ ಗಲಾಟೆ ಮಾಡ್ತಿದ್ರೆ Still it doesn't matter. ನಾಲ್ಕು ಜನ ಗಲಾಟೆ ಮಾಡ್ಕೊಂಡು ನೀನು ಬಿಡ್ಬೋದು. ಎಲ್ಲರೂ ಗಲಾಟೆ ಮಾಡ್ತಿದ್ರೆ is a problem. Out of 100, if 2 noisy things are there, it's okay. 98 is all right. So the qubits are equivalent to individuals. It will get prone to the noisy environment, but I am interested when I make a measurement, my information should be secured. I want to maintain the integrity of that. What I do, instead of having 1 qubit, I group 10 qubits as 1. Through a software, I call it as a abstract data structure called the logical qubit. You got my point? I define what is called a logical qubit, where a group of qubits I represent by using a software abstract, what is called a logical qubit. I manipulate only logical qubit. If one of them, out of 10 qubits, if one of the qubits get disturbed, doesn't matter, still the integrity is maintained because I am able to correct that information within my. So what is required is finally the integrity of quantum information can be maintained defining what is called logical qubits, where your error correction and reduction can be reduced. So challenge is to define logical qubit through a software abstraction. Okay, next. So this is what already I told you. Next. Now this is what I told you. If you look at the summary, the qubits are actually physical hardware based. Logical qubits are hardware and built from a quantum hardware, whatever electron systems. The second one is multiple physical qubits are used to that. Stability, the physical qubit is prone for errors and error corrected and more stable, and stability is required. Many physical qubits per logical qubit. For one logical qubit, I may use 10, 20 depending on the implementation. Next. So there are different kind of resistors. Okay, these are the classical resistor, entangled resistor, QAM and next you go. Next. Madam, next. Next. Yeah. Now, I will come, see I have told one property, superposition. Next I come to another important property which has got lot of applications in quantum communication, quantum information processing, what is called interference. Now, for example, I am here, I am a light source, okay? I am asked to pass through a slit. For example, Shashidhar sir is the destination, say. So in order to reach Shashidhar sir, I can come like this and reach him. This is one path. To reach him, Alinda, I can come this way also. I am a photon, I can come like this also. So to reach Shashidhar at the end point, I can take multiple ways to reach the end point. So when I am traveling, like a photon, I can go like this, I can go like this, I can go straight. While I am going, these photons, I am a light photon, each photon will interfere with each other. Okay, when I interfere, whatever the two photons interfere, they may add in such a way, it aids what is called the constructive interference, useful. Suppose if I have gone like this, I have gone in the opposite direction, both faces will get cancelled out, it is a destructive interference. So interference is another, so I may take a time delay, I may take 1 millisecond, from this side I may take 1.5 millisecond, there is a time delay. And also phase, what rate I am going, what phase I am going, the different shapes I can, so I can use the phase delay. The interference principle is extensively used for quantum communication and quantum information processing. Next. This is what I told. I have got a light source. The light is traveling across different directions. The end point I have reached. While reaching, these photons will interfere. Some of them will interfere in such a way that it aids. Some of them will move in such a way it distracts. Next. First one I am adding, that is two ways I am traveling. I've added, that is constructive interference. The other places, so now you understand the beauty of this quantum interference. The same concept is used in quantum algorithms. Constructive interference is used to find out the right solutions in Shor's algorithm or Grover algorithm. The wrong destructive interference points are used to reject the results. So while writing quantum algorithms, the constructive interference where interferer aids. I write a quantum algorithm using interference principles where the aiding things used to find out the right solutions. The destructive interference is used to knock out the unwanted solutions. That is what is done in Shor algorithm. Next. Yeah, the previous you go. These are what the quantum interference has got. I don't want to because it takes time to explain. So quantum gates and circuitry, it has got applications in quantum algorithms. It has got applications in quantum error correction and detection. Next you go. It has got application in quantum Fourier transform. It has got a lot of application in quantum equity secure information transfer. It has got, suppose when you have quantum networks, interference principle is used. Because I don't have time to explain because I said it's the information, each slide itself is a lot of information. Yeah, these are the applications you can. Next. Yeah. Now, this is a so I told about superposition, interference. Now listen this particular property, you listen it very, very carefully. What I am going to tell is not a science fiction. What I am going to tell now is not a science fiction, it is reality. Now, entanglement is a strange state out of which two particles are so deeply connected that they share the same existence when they are separated in space. If one of the state is changed, they automatically other state. Huh? Deepti? When you are set separately, you are represented by wave function 1, you are represented by wave function 2. I make them, ಇವರಿಬ್ಬರು ಫ್ರೆಂಡ್ಸ್ ಆಗ್ತಾರೆ, they start interacting. When they interact, I cannot represent both of them by separate function. ಎರಡು ದೇಹ ಒಂದು ಜೀವ. You got my point? ಎರಡು ಜೀವ, ಎರಡು ದೇಹ, ಒಂದು ಜೀವ. Means that I cannot separately tell Padmavati madam and Deepti madam separately. I have to treat them as one. So what is done? I will correlate their physical properties. One of the properties which you can correlate is the spin direction. The other property which I can correlate is the polarization state. The third property what I can correlate is the phase. I correlate these properties. Okay? So when I correlate this physical property, spin direction or the polarization state or the phase, no longer these two mediums can be treated separately. They have to be treated. Okay. The speciality is, once they are correlated, means that their physical properties are correlated, we call it as they are entangled quantum systems. The beauty of this is, I do not know Deepti madam is having upspin or downspin. I do not know Padmavati madam is having upspin and downspin because their properties are correlated. I do not know. Now I want to find Deepti madam is having upspin or downspin. I will make a measurement on Deepti madam. I will come to know that she is having upspin. Okay. Now, the moment I make a measurement on Deepti madam, she is having upspin, Padmavati madam automatically will come to know that I should have downspin. She will without doing anything. Okay. This is the beauty. Now, second one thing, by some means, I will keep Deepti madam on Earth. I will take Padmavati madam to Milky Way galaxy. By some means. Now when I take, they are separated by millions of light years. These are the two quantum systems separated by millions of light years. Their physical properties are still correlated. They are entangled. Now, I make a measurement on Deepti madam, who is on Earth. She is having upspin. Now, Padmavati madam, she is there in the Milky Way galaxy. She will immediately comes to know that I should have a downspin. She will immediately change. This is what we call it as quantum non-locality. You have an activity happening violating this theory of relativity. You understand? And second thing, now madam is having upspin. By some means I will change her spin direction from upspin to downspin. The moment I change her downspin, Padmavati madam, who is there in Milky Way galaxy, she will change into upspin immediately. Without information transfer. So that's why Einstein called it as a spooky action at distance. Some Yadav some Devarayara alien Kutbandi state. No, this is the way the fundamental particles behave at the atomic level when their properties are correlated. So entanglement is another important property which you use it in quantum computing. You got my point? Next. Next. This is what I told. Deepti madam is in Earth and Padmavati madam in Milky Way galaxy. So, two entangled particles where physical properties are correlated, they remain correlated irrespective of the linear distance. This property also used in superposition, interference, entanglement. If these three you have understood, 50% of your quantum computing you have understood. If these three you have understood, 50% of quantum computing you have understood. Mathematics anyway you need time. I don't want, because of lack of time, I don't want to go too much. Okay, now you understood? Next. Yeah, now maybe one thing, whether really it is possible to create an entangled system. There are so many ways. By spin interaction, using particle decay, by photon mediation, by parametric downconduction. Next you go. Next. By superconducting system, using quantum dots, using Bell state generator. That's probably where they can create an entangled particles. Each of them needs an explanation. Because I don't have time, I want to tell you it's not a science fiction, it's a reality. So, two quantum systems which are entangled, they remain entangled forever, irrespective of the linear distance. So Einstein was not able to explain. There was a great argument between Niels Bohr and Einstein. Finally, they came out with what is called the EPR paradox. Einstein, Polonsky and Rosen is a Russian scientist. So they came out and he said that quantum mechanics is completely, you are not able to explain. Finally, it is proved that what Einstein proved is the way in which Einstein looked at it is wrong. So he came out with what is called hidden variables. There may be something which we are not able to explain. He is not able to explain. Here is a activity going on where an information transfer, an activity going on beyond the velocity of light. Okay, no particle in the universe can travel greater than the velocity of light. That is your theory of relativity. It is violating this. This is an instantaneous action. So that's why it is called quantum non-locality. So these three. Next. Yeah. Now what are all the practical challenges? There are challenges actually. So say electrons must be isolated from the environment to prevent void, otherwise if it gets interacted with the thermal environment, the entangled will get disturbed. That is a challenge. Second is control. Precise control means that the interaction between the electron is required to achieve that, because the electron is going around the nucleus with a speed equivalent to velocity of light. Now, external probe, where we are giving a query to find out the position of the electron, whether it is going upspin and downspin. After changing again, making a measurement, that is really a challenge. You can understand the response time required. It will be in some nanoseconds. You got my point? Making a query to find out the position of the electron, having upspin and downspin, changing the electron direction and taking decisions all these things, well, now you can understand this, the complexity of a quantum memory where the spin direction, what you want to go into store, you will show sufficiently long enough so that you can make decisions. Otherwise it will get decovered. The information is lost. Okay, next. Yeah, this is one thing. I talked about only one property called spin direction. Instead of one property, I can correlate multiple properties to make my information more secured. Okay? So that will have a lot of, in the quantum information transfer, where 2 bits can be combined into a single one and transmit across the quantum network. We call it as superdense coding. So that improves your quantum information capacity. Okay? So hyperentanglement is a phenomenon where particles entangle in multiple 3D subassemblies. So I can correlate the phase, I can correlate the spin, I can correlate the polarization also simultaneously. So that your security of whatever quantum cryptography you call will become more secure. Next. Yeah. So now, another one is one more law, just I'll touch upon. Now, these light photons, no, they travel from place A to place B. Like I gave an example, Shashidhar sir. When I go, the light photon, I may take different shapes. Okay? I may take a circular shape, I can take a Gaussian shape. So the distribution of photon from going from place A to place B, I can take different shapes to reach the end point. Okay? Now the spatial modes can be manipulated using the external source. Means that the shape of the photon going from place A to place B can be manipulated to store, retrieve and transmit information. So now 4 properties I have told. One is the spin direction, second one is the time delay, the interference, third one is the polarization, last one is the spatial modes, where the shape of the photons, that is becomes a basics for the photonics, which is the realistic for having a quantum computer of a laptop in future. The spatial mode manufacturing, probably maybe 10 years from now, you will have a photonic quantum computer like a laptop. Okay, so photon, that's what I explained. Next. So it has got applications in quantum communication, quantum imaging. Like for example, you have got PET, so all these quantum imaging enhancement can be done faster. You got entanglement. Next. Yeah, next. Yeah, the application of quantum entanglement is what is called quantum teleportation, where an information is transferred from place A to place B without physically transmitting the information. Where quantum states like polarization state or the spin direction or the spatial modes are transferred, and finally this quantum information sent from source to the receiver, they will receive this information, they form a secret key, then their secret key they can use and encode an information, send the information through a classical channel, either a telephone or a mail. So the application is quantum teleportation. Next. Yeah, this is the way. Actually I need 5 minutes to explain. There's a lot of information is there. How the quantum teleportation works, I have this, how it is done, it needs another 10 minutes to explain. So I don't have time to explain. This is the diagram, what kind of hardware, how it is done. It's very beautifully explained. What kind of optics is used, what kind of detectors are used. Okay, what information is transferred from place A to B. So we share the quantum information from source A to, but still use a classical channel after encoding. That is quantum teleportation. Next. Yeah. So now I just touch upon what is quantum computer. See, a quantum computer information is stored in the coefficients already I told you. Quantum computer is a device that can manipulate information, so that a controlled manipulation of a quantum state is called quantum operation. The device which performs a quantum operation is called a quantum gate. What I told like OR gate now. Next. See, basically, like electronic hardware, you have these quantum gates, they are not physical gates. Please understand, like logic gates what you have in electronics like OR gate, AND gate, NOR gate, exclusive OR gate using K-maps and all these things, they are not physical gates. These are all mathematical operations done on a quantum system to change the state of a qubit. Basically they are all unitary matrices. We apply a matrix to change that. Okay. But actually you don't need to know the mathematics. But when you want to write programs or quantum algorithms, you should know the mathematics to understand which gate to apply. Okay? For that reason you need this. Otherwise you don't need, because the whatever simulators IBM which gives a library to give directly gives the call to the gates. Whether it is a hard-mode gate or a Tuffley gate or different gates are available. They're all mathematical gates. You can just give a call, like a procedure call you can give. Call H means it will give. Okay, so next. Yeah, 1 second, please go. Previous. Yeah, there are, I don't want to explain too much, it will be too, with this I will stop actually. There are quantum gates which are called the Pauli gate, control NOT gates, Tuffley gate, Harmad gate. Harmad gate is a gate where we want to create superposition of qubits. Harmad gate is used. And when you got two qubits to manipulate, there is a particular gate. When you got 3 qubits, where the state of the third qubit I want to change based on the state of the first 2 qubits, there is a CC0 gate is available, Tuffley gate. With 3 qubits, there is a gate. So like that, little bit mathematics is there anyway. Because of paucity of time, I don't want to go into the mathematical details. You please go little further. Next. Yeah. Once a previous hogi. So now, how to build a quantum computer, a conceptual quantum computer? See what I do. I can have a qubit can be prepared in some known state, means that an electron can be prepared in some known state having a ground energy and ion energy. Each qubit can be measured in the basis state. It can be, I can make a measurement whether it can be there in the lower energy state or a higher energy state. A universal gate, a set of quantum gates can be applied to change its direction. In classic circuit, the logic gates are applied sequentially. Okay? Whereas in quantum circuit, logic gates are applied sequentially as a part of qubits. Next. Yeah, okay, previous. Yeah. This is very important for you. ATM ಎಲ್ಲ ದುಡ್ಡು ಡ್ರಾ ಮಾಡ್ತೀರಾ ಅಲ್ವಾ? ನಿಮ್ಮ ಹಣ ಸೆಕ್ಯೂರ್ಡ್ ಆಗಿದೆಯಾ? Are you sure that your money is safe? ATMs, you know what is the security is used? What kind of security is there? ಯಾವ ಧೈರ್ಯದ ಮೇಲೆ ATM ಅಲ್ಲಿ ದುಡ್ಡು ಡ್ರಾ ಮಾಡ್ತೀರಾ? Anybody? No, can you say what is the security guaranteed for withdrawal of money there? Computers expect to answer. So it uses RSA algorithm. Okay, that is the security. Now, in the classical computers, that is ATM, the security of the ATM is depend on the computational complexity of a mathematical problem, thinking that factorizing large numbers is intractable. It is not possible to factorize a large number, it may take hundreds of years. So the algorithm used in that ATM security, that is initializing a very large number, it will take hundreds of years to factorize. So with that assumption, RSA algorithm is implemented in ATMs. Now, you may ask a question, really quantum computers are powerful compared to classical world? My answer is no. There are problems in the world. We can represent it as a qubit problem, which will solve the real world problem in no time, where the best available supercomputer in the world will take thousands of years. Now I will give an example. I will come to the example of ATM. ATM security is based on Factorizing large number is impossible. It will take 100 years. That is the security, which is the security code is written. Now, that security code what is written can be translated into a qubit problem using Shor algorithm, quantum algorithm. I can crack that ATM security in few minutes. Okay, ATM security at risk now. Okay? So now so one of the problems I told about RSA algorithm, so people are looking for what is known as quantum resistant algorithms. Okay? So that is another application. So you got next. Yeah. See normally conventional memory memory normally like PROM, ReROM, memory memory corrupt you cannot retrieve the data. Correct? When memory corrupt you cannot retrieve the data. Whereas in quantum memory, we can retrieve the information, even corrupt and partial information. That is the beauty. Whereas in conventional computers, you need actually an address table. I have to give a request, I do an address translation and fetch the data. There is a limitation. Each time you have to go on augmenting the memory from 5 GB to 10 GB, 10 GB to memory. Okay, there is a limitation in quantum conventional memory. Whereas quantum memory, you can retrieve the information from partial and corrupt data, and storage limitations are not there. Next. Yeah. What are the ways we can generate quantum memories? You have got atomic systems. Atoms are ion trapped and manipulated using lasers. You have quantum memory. You got solid state systems. You got photonic systems. Next. This is the kind of hardware where quantum memories are there. These are the quantum memories which are going to be used in quantum networks and quantum internet, what is being talked about. These are the kind of hardware where you have to keep the temperature as low as 4 degree Kelvin. That is another challenge. Next. Yeah, these are the challenges. One is the quantum state, error correction, decoherence. So with this, I will stop. I will go to the application part of what are all the computing application in AML and DL. Okay, here I will stop because it minimum actually 2.5 hours break is required. I will stop this and go to the next slide. Madam Nelly. Quantum computing AI close market. Next again. In close ಮಾಡಿ ಹೇಳ್ತೀನಿ. ಅಲ್ಲ ಆ ಫೋಲ್ಡರ್ ಬಗ್ಗೆ ಕ್ವಾಂಟಮ್ ಕಂಪ್ಯೂಟಿಂಗ್ ಇನ್ ಎ ಅಂಡ್ ಎಮ್ ಎಲ್ ಅಂತ ಇರಬೇಕು ನೋಡಿ. ಕ್ವಾಂಟಮ್ ಕಂಪ್ಯೂಟಿಂಗ್ ಇನ್ ಎ ಅಂತ ಒಂದು ಫೈಲ್ ಇರಬೇಕು ನೋಡಿ. ಅಷ್ಟೊಂದು ತುಂಬ ಫೈಲ್ಸ್ ಇದೆ. ಕ್ವಾಂಟಮ್ ಕಂಪ್ಯೂಟಿಂಗ್ ಇನ್ ಎ ಅಂತ ಇರಬೇಕು ನೋಡಿ. ಕ್ವಾಂಟಮ್ ಕಂಪ್ಯೂಟಿಂಗ್ ಇನ್ ಎ ಕೆಳಗಡೆ ಇರಬೇಕು ನೋಡಿ ಮೋಸ್ಟ್ಲಿ. ಕ್ವಾಂಟಮ್ ಕಂಪ್ಯೂಟಿಂಗ್ ಅಪ್ಲಿಕೇಶನ್ ಇನ್ ಎ ಅಲ್ಲಿ ಇದೆಯಲ್ಲ, ಕ್ವಾಂಟಮ್ ಕಂಪ್ಯೂಟಿಂಗ್ ಇನ್ ಎ ಅಂತ ಇರಬೇಕು ನೋಡಿ. ಇಲ್ಲಿ ಟೆಕ್ನಾಲಜಿ ಕ್ವಾಂಟಮ್ ಕಂಪ್ಯೂಟಿಂಗ್ ಎ ಹಾಗೆ ಅದು ಆಗ್ತದೆ. So, till now what I have told, 3 fundamental properties: superposition, interference, entanglement, the properties like phase, spatial modes, polarization. If you know this, the challenge is to store this information sufficiently long enough in a quantum memory so that you can make decisions. I just wanted to show one quantum computer actually. Maybe after this at the end I wanted to show IBM quantum computer. Anyway, after this I will just come back and I will show I have got all the quantum computer in the chips available. In fact, lot of what are the IBM is doing, what Microsoft is doing, lot of information is there. I will show one quantum computer and India's first quantum computer, which is a Bangalore-based quantum painless. No? I have the photograph. I will show that. Okay. Hey, adalla madam. ನೀವು ಎ ಟೈಪ್ ಮಾಡಬೇಕು, ಮೆಟ್ರಾಲಜಿ ಇಲ್ಲ. ಎ ಅಂತ ಇರ್ಬೇಕು ನೋಡಿ ಮೇಡಮ್, ಅಲ್ಲಿ ಕಾಣಿಸ್ತಾ ಇಲ್ವಾ? ತುಂಬ ಇದೆ. ಕ್ವಾಂಟಮ್ ಕಂಪ್ಯೂಟಿಂಗ್ ಇನ್ ಎ ಅಂತಿದೆ ನೋಡಿ. ಕ್ವಾಂಟಮ್ ಕಂಪ್ಯೂಟಿಂಗ್ ಅಪ್ಲಿಕೇಶನ್ ಇನ್ ಎ ಅಂತಿದೆ, ಸಿಗ್ತಾ? ಕ್ವಾಂಟಮ್ ಕಂಪ್ಯೂಟಿಂಗ್ ಅಪ್ಲಿಕೇಶನ್ ಇನ್ ಎ ಅಂತಾನೆ ಇದೆ. ಸಿಗ್ತಾ? ಒನ್ ಆಫ್ ದಿ ಫೈಲ್ ಏನು ಎ ಅಂತಿದೆ ನೋಡಿ, ಹಾಂ ಅದು ಹಾಕಿ. ಹಾಕಿ ಅದೇನೆ ಸ್ಲೈಡ್ ಮೋಡ್ಗೆ ಹಾಕಿ. ಒಂದು ನಿಮಿಷ, ನೆಕ್ಸ್ಟ್ ಎಲ್ಲ ಹೇಳೋತೀನಿ. Okay, quantum computing story. Let us look at, I'll just briefly touch upon because so many applications are there. I just touch upon, I am not going deep into the subject part because the algorithm parts of your individuals may be much familiar. I'll just touch upon the application part. Okay, next. Yeah, quantum computing has a lot of potential to leverage AI. What are all the reasons? One is the speed and efficiency because your qubits can process information where they can all the states simultaneously. It can have massive parallel computation, and you have got quantum entanglement which allows qubits to correlate forever so that you enhance the computation power. You can handling complex problems, particularly for solving optimization problems, common AI tasks like neural network training and the decision making. And similarly, you have got the high dimension data sets where machine learning and models and data sets are essential. Next. See, enhanced quantum algorithms such as like quantum subordinate information or quantum neural networks actually, they provide exponential data for training. The more data you train, you get the more speed up. So training of the data and inference time make this computing becomes very handy, and particularly the data sampling, because data sampling is another important factor in algorithms. So quantum computing performs certain tasks like data sampling, data clustering, and the feature selection, improving the performance AI models. And you have got what is called the quantum Monte Carlo method can be used to simulate distribution, training the data. So there is an application. Next. Yeah. So the quantum computing actually transform. See now with problems. See optimization. See what I till now, which is called the gate-based quantum computing. There are different models of quantum computing. One is what I talked about is called gate-based quantum computing. There is another way of taking what is called adiabatic quantum computing, which is done by what is called quantum unveiling, where I represent the problem as an energy function and try to find out the minimum energy function. What is called adiabatic computing. There is another computing where Microsoft is doing topological quantum computing, where they try to represent information globally where errors are less. Okay, so they are having invented a special conductor, a proper conductor, where they generate an exotic particle called Morona, which doesn't exist in the world. Under certain conditions only, that exotic particle gets generated, called Morona 1. Either it is a liquid, nor a solid, or a gas. It is an exotic particle. So topological quantum computing is another area. So what I talked about optimization problem, D-Wave Systems, which is a US company, they have generated hardwares are available up to 1000 qubits. So optimization problems, which are minimizing loss functions, resource allocation, dissemination, and even the quantum approximation, QIA and quantum annealing, basically you have the hardware available. So it has got application in supply chain optimization, particularly when you are logistic route chain planning, you can have, and financial portfolio optimization. For example, when you are having a stock market, so that is having dynamic pricing strategies for e-commerce companies. So this is application for optimization problems. Next, machine learning algorithm. Because of quantum computing can actually speed up machine learning, the training and inference. See, you have a traditional machine learning algorithm like SVM, neural networks, and clustering methods. But applications you have faster training of the deep learning model for image and speech recognition, particularly lot of application. Quantum enhanced generative models like if you want to create creativity on music. So there is an application, improved feature selection for dimensional reduction in multiple dimension data set. And while processing, quantum computing is applied to NLP for a text summarization or ChatGPT. You can have a quantum models, and particularly quantum kernel methods can process large linguistic space more efficiently than classical. And you have the applications demanding search, enhancing like the search engines of GPT and complex text calculation for log data sets. You have application in reinforcement learning. So basically, AI models that learn through trial and error methods, quantum algorithm expose fast action and make spaces. So it has got applications in real time. For example, actually I have traveled driverless vehicle. So there this is applied. I have got a video also here. I have traveled 5 kilometers. A driverless vehicle, an autonomous one, completely AI driven. I have driven through Tesla's in US for in San Francisco. I have driven. I sat in the vehicle. It drove me. It parked also. All your models is done through this. Not quantum, it's AI. Quantum AI is possible. So, real-time decision making for autonomous vehicles and drones, robotics for efficient task automation. You have got game AI capable of solving complex scenarios. So, you have got quantum coming into picture. Next. So, quantum neural networks actually is a prominent area where quantum circuit emulate the structure of traditional neural networks. These models improve the scalability. So, AI models, particularly, you have a COVID-19 simulating one vaccine, it took 2 years. Suppose if you have a quantum computer, it is very easy to simulate protein folding of multiple dimensions which classical computers cannot do. So particularly protein folding and new drug discovery for any kind of this is possible using AI models, and personalized problem where you have a unique kind of disease using quantum computing and the AI models, one can generate the personalized medicines for that. You need a data sampling and clustering, and quantum algorithms like quantum amazing. They are ideal for sampling large data distribution, particularly genomics and but in the healthcare application you have got market segmentation of business analytics, image data, video compression, you have got the application of next. And quantum support vector machines basically have got the applications related to medical diagnostics using enhanced pattern recognition. You have image processing. You have got fraud detection in financial transaction, and for climate modeling, particularly weather prediction, you have got a lot of application AI models, and improved cyber security. Quantum computing and AI models using cyber security. So you have got application in quantum security for sensitive communication, for detecting and predicting cyber attacks in real time, and data sharing on large data systems. Next. And drug discovery in healthcare, already I told you, protein folding and personalized medicine and optimizing clinical trials and recommendation systems. For example, if the AI model can suggest a particular thing, looking at the market survey to say that which product you should buy. Okay? So particularly personalized recommendation for e-commerce product. You have got improving element of streaming of Netflix, which one you should see. It's particular. So Netflix and other things, enhancing custom relation strategy market, product to be reached to many people. This is possible using quantum AI. Next. Autonomous systems, basically quantum computing in real decision making systems, self-driving cars, and so traffic flow optimization in autonomous vehicles. You have got an application. You have got multi-robot coordination warehouses for manufacturing plants. You have got dynamic adoption of changing environment autonomic agents, and climate and energy solutions, particularly the grid optimization of energy sources you have got, and particularly quantum climate models for accurate prediction, resource allocation for conservation parts. Next. But what are all the challenges? I talked about the applications. All of them as on today are the possible things, but not in real as on now. These are all the applications what I have. Now, what are the limitations? A limited hardware. As of quantum computers are not fully scalable, not error-free. So, it has not come to a conceptual stage where a common man can use. Second thing, the noise and decoding. Quantum systems are sensitive to environmental noise, which can lead to That is another challenge. The algorithm development, many quantum algorithms, machine learning, they are in the research stage. Fourth one is, in future, you cannot have classical systems alone, you cannot have quantum systems alone. Certain jobs has to be done by a classical system, certain jobs has to be a quantum system. You need a hybrid system of quantum computers, classical system, you need a pipeline of an interface. Where the quantum computers you have to maintain a temperature of a cryogenic temperature of 4 degree Kelvin. You have a hyperplane separating that, where Microsoft is doing that. Hybrid quantum systems. So skill gaps. Basically, the biggest problem is quantum computing is not the property of physics. Physics knowledge is required. It needs knowledge of physics, it needs knowledge of electronics, it knowledge of quantum optics, it needs knowledge of lot of mathematics, of particularly expertise in linear algebra, it needs knowledge of solid state physics, it needs knowledge of particle physics. You need good computing background. For your information, now today we are talking about AI, ML and DL, which is driving. Please understand, from now, if you don't awake over above AI, ML and DL, there is a quantum sitting. You have quantum at the top, all the three are below. You have got quantum AI, you have got quantum ML, you have got quantum DL. So you have to expertise your skill set, you have to enhance. Taking either there are actually IIT Delhi is offering online courses. One can register postgraduate diploma in quantum technologies available. So along with your course you can enhance your skill set. Believe it or not, 5 lakhs jobs are available in India, but there is no expert. 5 lakhs jobs, very high paid jobs are available on quantum technologies. But you don't have a proper trained quantum technologist available. And people will get scared the moment you look at quantum mechanics and mathematics. No. I am not a quantum expert. I had a physics background, I had a computation experience, I have a passion for learning. I put effort and learned. Nothing is difficult. I have handled classes for MTech classes on quantum communication, which I am not knowing at all. So what is need is, you have to change your skill set, get the skill set written. So your conventional way what of degrees will not help. So 10 years from now, along with whatever you have to extend the changing technology you should underscore. So you have to acquire proper skill sets. Okay, so next. So quantum machine learning actually integrates quantum computing with traditional, so you have what is called quantum data encoding, which is called quantum feature mapping. So classical data can be transformed quantum state to quantum feature maps. You have quantum kernels for support vector machines and quantum speed up optimization. See, basically there are ML models like gradient descent, quantum algorithms such as QA and VQE offer speed ups for optimization problems. You have quantum enhanced kernels. Next. And quantum neural networks and quantum remotes, we have got the application. Next. Yeah, you have got application in quantum deep learning, DNNs, which is called deep neural networks. You have got application in quantum variation circuits of deep learning. You have got application in quantum Boltzmann statistics. You have got quantum generative models, and you have got quantum tensor networks. These are the applications in deep learning. Next. So the advantage of quantum computing in ML and DL to speed up. You have got an expansion in quantum parallelism enables faster computation. You have got quantum algorithms will improve optimization and neural network training. Quantum feature mapping improves data classification. Quantum sampling helps generative models to train better. Quantum computing can process complex and high dimensional data effectively. Next. And challenges. Hardware limitation. As an quantum computer on early stage with limited qubits, you have got noisy quantum systems and algorithm development, hybrid system. So quantum computing has the potential to transform ML and DML by enhancing speed. So practical implementation is still evolving, and so a lot of potential is there. So these are the kind of applications. And last one, the 10-minute slide I want to show why you should go for quantum computers. What is the time frame which you can expect a desktop of quantum computing which can come in India? I got, with my ingenuity, I have prepared few slides. Madam, need of going to quantum computing module ಇದೆ. Need of going to quantum computing ಅಂತಿದೆ. ಅದನ್ನು select ಮಾಡಿ, close ಮಾಡಿ. So these are the kind of lot of applications are there. I have just listed few. I have got the AI models from biotechnology and space biology. I have got lot of applications in space biology, drug discovery. I have given a talk to biotechnology students. Space biology, lot of applications are there. When you send astronauts, lot of applications are there. But I have not told this actually because I don't have time. So last 10 minutes, madam. This is why you should go to quantum computing. At the end, I want to show one video. Whatever I have told the story now for half an hour, the video will help you to understand better. Okay? This 10 minutes, this way. Afterwards, 10 minutes video. Whatever I have told, you will understand. You will understand better by looking at the video. Whatever wave function I told now, when you look at the picture. Madam, okay, madam. Sorry. Yeah, why we should go from classical computing to quantum computers? One is the computational parallelism, ability to represent multiple states simultaneously. Okay, why it matters? Because n qubits can represent 2 to the power of n states simultaneously, which is not possible in conventional computing. Certain problems scale exponentially in classical system and polynomially in quantum state. For example, 50 qubits, you have 2 to the power of 50 states. That is the computing power 1 quadrillion. Okay, impossible to simulate classical computers. Massive speed up for specific problems. Next. ಹೋಗ್ತಾ ಇಲ್ವಾ? ಅಲ್ಲಲ್ಲ, ನೀವು ಹಳೇದ್ರಲ್ಲೇ ಇದ್ದೀರಾ. ಹಳೇದಕ್ಕೆ ಹೋದ್ರಿ. ಹಳೇದು ಕ್ಲೋಸ್ ಆಗಿಲ್ವಾ? Because when I went to college, returning from US, I was not in India, I was in US for 6 months. In fact, this visit I had an opportunity to visit 3 top US companies in the world. One is I had been to Google headquarters, I have visited Apple headquarters, I have visited eBay headquarters. In fact, I had an experience of virtual reality. Normally the product is not available in India. $15,000. I was, so the simulation they did, they took half an hour to map my eye coordinates, my eyes and other things in space. Finally they took me to the top of Empire State Building, ಅಲ್ಲಿಂದ ಹಾಕಿದ್ರು ಬೆಳಗ್ಗೆ ಬಿದ್ದಂಗೆ. ನನ್ನ ಹೃದಯನೇ ಬಾಯಿಗೆ ಬಂದ್ಬಿಡ್ತು. ಒಂದು ಸಡನ್ ಒಂದು ಡೇಸ್ನೆಸ್ ಆರ್ ಬಂದು ನಾನು ತಿಂತಾ ಇದೆ ಅದು. So virtual reality, that was a really fantastic experience for an Apple product which is not available in India. So I had a demonstration in Google headquarters. One of my son-in-law's friend arranged that virtual reality. That's the breathtaking experience. The product is too expensive, $15,000, so around 10 lakhs, and it's not sold in India. Okay, so their culture is completely different, and the workbenches, the kind of whatever I have visited here, but their expectation is different. It's highly demanding. If you are not competent, not updating your technology, next step is unless you have got telling you US is not a country to live. And everything comes with money only. ಅಲ್ಲಿ ಯಾವ ಕರುಣೆನೂ ಇಲ್ಲ. ವೆರಿ ವೆರಿ ಹಾರ್ಶ್. ಆಯ್ತಪ್ಪ, ಪ್ರೀವಿಯಸ್ ಹೋಗಿಪ್ಪ, ಪ್ರೀವಿಯಸ್. ನೆಕ್ಸ್ಟ್ ಹೋಗಿ. Yeah, quantum entanglement. See, actually entangled qubits behaves like a system, a single system. Measurement of one instantly affect the other. So enables experience. So example, quantum teleportation, quantum error correction, multiple gates outperform classical circuits. Next. See now, algorithmic speed advantage. I already told classical algorithms, it is exponential. O of n ಅಂತ ಹೇಳಿದ್ರೆ oracle of n ಅಂತ. O of n ಅಂತ ಹೇಳಿದ್ರೆ oracle of n ಅಂತ. Oracle is an object actually to find out the possible paths. So in this case, quantum algorithms, a polynomial here is root of n and it is polynomial. So why it matters? Because for cryptography, drug recovery and material science optimization, this property is very, very useful. Next. And simulation of nature. When you want to simulate nature, okay, native compatibility of quantum physics, nature itself is quantum mechanical, and particularly chemistry, molecular orbitals, high temperature superconductors, and nuclear and particle physics. It needs next. Energy efficiency, particularly if you have a grid, okay. So Moore's law slowdown and all data centers. Next. Next. Now, what is the challenge whether a quantum computer, why you are not able to have a quantum computer as on today in a room temperature? Because the operating temperature now superconducting units, the temperature you have to maintain is 10 to 20 degree millikelvin below sub-zero temperature. Cryogenic temperature you have to maintain. Number one, requires a special refrigerators called dilution refrigerators, which is quite expensive. Required for common use, operating temperature is room temperature or more than 77 degree Kelvin. So, what are all the possible candidates to get a quantum computers like a laptop? The candidates are photonic qubits, you have got diamond memory centers, and topological qubits. As on today, the Microsoft is doing the research. As on today, they have a chip. So, in fact, remove bulky cryogenic systems, enable desktops can devices. Next. Next. Yeah. So now, coherence time is nothing but, I told you, no, the electron goes from lower energy state to higher energy state. How long it can stay? The more longer you stay, it is useful to you. You can make decisions. So as on today, supercomputing to make the coherence time, it can stay only for 100 microseconds. Beyond 100 microseconds, the information is lost. But for normal use of computing, you need required for desktops of seconds to minutes. That coherence time should be of the order of seconds to minutes, not in microseconds. So you need that much level of improvement in coherence time. Unless you reach that, you cannot have a desktop of quantum computer like this. So more operations before errors. Means errors should be reduced. Few corrections also you should minimize. Next. And error rate and see, basically we call it as gate fidelity. When I do a quantum operation, how accurate is my quantum operation? That is important. So if a gate fidelity is 1, my quantum operation is 100%. If it is in between, that much error is there. If 0.6 means 40% error is there. Gate fidelity. Gate fidelity will give you what is the accuracy of your quantum operation using a quantum gate on a quantum system. So gate fidelity, currently the error rate is of the order of 10 to the power of minus 3 to 10 to the power of 7, and you need around 1000 physical qubits. The error rate what you are getting. But for conventional laptops or the computers, the error rate should be less than 10 to the power of minus 6. Unless the error rate you bring from 10 to the power of 4 minus 4 to 10 to the power of minus 6, you cannot achieve quantum computer of laptop. Second one is logical qubits. Now, for one logical qubit, you need 1000 physical qubits as on today. To have a laptop of quantum computer, you need one logical qubit is equal to one physical qubit only. That should be scaled down. So, impact smaller machines, reversible everyday computation. Next. So, today, qubit scalability means today you are able to scale the quantum computer with the qubit processors. You have got 50 to 1000. Now, for useful applications for a common man, you need around 1000 logical qubits which are required. Unless you have 1000 logical qubits, you cannot have a desktop. So finally, modular chip integration and CMOS compatible fabrication is required. Next. So finally, you need a hybrid architecture. Future desktop quantum system, what it can look like, you have a classical CPU, you have a GPU, a quantum coprocessor, and quantum handles the optimization kernels, cryptography, machine learning algorithms, emulation tasks. So analogy, GPU today in a desktop, and quantum processing equivalent GPU. QPU, it's called QPU. Instead of CPU, we call it as QPU. Next. And software abstraction. Currently, as on today, anybody wants to come to quantum computing, you need physics knowledge. Without quantum mechanics knowledge, you cannot do. So minimum quantum mechanics knowledge, skill set you have to do. Second, low-level quantum circuits. You should be able to translate that problem into quantum circuits. So you should learn how to translate. And you should also know about computer science fusion, high-level languages and compilers also should know. Automatic error mitigation, like different kind of error codes are there. Fat codes, short codes, so many error correction codes are there. So error coding you should learn. OS level quantum scheduling one should know. So target experiences you have to run, optimize, simulate and solve. When you go for this, no physics knowledge is required. Next. So in cost, as and today, current you need millions of dollars. And high power is also required for cooling. Power consumption by the quantum chip is very low, but cooling you have to spend a lot of money. So costs are comparable to high-end GPU, power less than 100 watts. Few hundred watts is required for a laptop of quantum computing. Next. And security. Fine, okay, next you go. Next. So what is the realistic, with my knowledge, as and today, where we stand, quantum cloud. Now IBM is giving all the companies are offering quantum processors over the cloud. By 2030 via internet you will be able to access doing quantum processing. You can also have hybrid servers by 2035 and enterprise quantum servers. And quantum accelerator by 2045 in the workstation, probably by 2045, by 20 years from now, you will have desktop quantum computers. That is my vision, and I think it is possible from 20 years from now, you will have a quantum desktop. Okay, close. Video. So this is what somebody asked question, I have put a lot of effort in making this. Quantum computing is really quantum computing presentations in the achievement. Quantum computing videos and presentation in the ಒಳಗಡೆ ಇದ್ದೀರಾ ಹೊರಗೆ ಬನ್ನಿ ಒಂದು ಬ್ಯಾಕ್ ಬನ್ನಿ ಡೇಟಾ ಝೀರೋ ಹೋಗಿ ಕ್ವಾಂಟಮ್ ಕಂಪ್ಯೂಟಿಂಗ್ ವಿಡಿಯೋಸ್ ಇರಬೇಕು ನಿಮ್ಮ ಫೋಲ್ಡ್ರು ನೀವು ಕ್ವಾಂಟಮ್ ಕಂಪ್ಯೂಟಿಂಗ್ ಪ್ರೆಸೆಂಟೇಷನಲ್ಲಿ ಇದ್ದೀರಾ ಹಿಂದಕ್ಕೆ ಬರಬೇಕು ನಾನು ಅದನ್ನು ಹೇಳ್ತಾ ಇರೋದು ಮೇಲ್ ಡೇಟಾ ಝೀರೋಗೆ ಹೋಗ್ಬಿಟ್ಟು ಡೇಟಾ ಝೀರೋ ಹೋಗಿ ಅಲ್ಲಿ ಎಕ್ಕಿಗೆ ಹೋಗಿ ಡೇಟಾ ಝೀರೋಗೆ ಹೋಗಿ ಇಲ್ಲಿ ಕ್ವಾಂಟಮ್ ಕಂಪ್ಯೂಟಿಂಗ್ ವಿಡಿಯೋ ಅಂತಿದೆ ನೋಡಿ ಅಲ್ಲಲ್ಲ ಕ್ವಾಂಟಮ್ ಕಂಪ್ಯೂಟಿಂಗ್ ಪ್ರೆಸೆಂಟಿಂಗ್ ಅಲ್ಲ ಒಂದು ನಿಮಿಷ ಬೇಡ ಕ್ವಾಂಟಮ್ ಕಂಪ್ಯೂಟಿಂಗ್ ವಿಡಿಯೋ ಇದೆ ಕಂಪ್ಯೂಟಿಂಗ್ ವಿಡಿಯೋ ಇದೆ ನೋಡಿ ಅಲ್ಲಿಗೆ ಹೋಗಿ ಅದರಲ್ಲಿ ಎಂಟ್ಯಾಂಗಲ್ಮೆಂಟ್ ಏನೋ ಇರಬೇಕಲ್ವಾ ಅದು ಹಾಕಿ
Quantum mechanics sometimes looks like an assorted mix of weird stuff. There's wave particle duality where quantum objects sometimes look like little compact particles and sometimes like spread out waves. There's superposition, where the object seem to be two things at once. There's the uncertainty principle, which says that the universe seems to conspire to stop us from knowing every detail of a quantum object. And then there's entanglement. Albert Einstein famously described this as spooky action at a distance, where doing something to one of a pair of entangled particles. Quantum mechanics sometimes looks like an assorted mix of weird stuff. There's wave-particle duality, where quantum objects sometimes look like little compact particles and sometimes like spread out waves. There's superposition, where the object seem to be two things at once. There's the uncertainty principle, which says that the universe seems to conspire to stop us from knowing every detail of a quantum object. And then there's entanglement. Albert Einstein famously described this as spooky action at a distance, where doing something to one of a pair of entangled particles seems to instantly affect the properties of the other, no matter how far away it is. Now, the truth is that none of these descriptions of quantum phenomena is quite right. They're all really just efforts to use our everyday language to talk about things that can't quite be described by it. That's especially true of entanglement, which is not spooky action at a distance at all. It's something that is difficult to describe with our everyday intuition. But it's worth trying to understand it because, as Erwin Schrödinger said, it is the characteristic trait of quantum mechanics that enforces its entire departure from classical lines of thought. In addition, entanglement is the key ingredient of the newfangled technologies we keep hearing more and more about. Super powerful quantum computers and uncrackable data encoding using quantum cryptography. It's about to become very real for everybody. So what the heck is quantum entanglement? I think that with a few illustrations and animations, we may yet be able to understand it a little bit better. And that's coming up right now. Entanglement sounds sort of like entangled pairs of people. If Alice and Bob get married, they literally become entangled by tying the knot. Suppose that then Bob tragically dies. Alice goes from being a wife to a widow. What happens to Bob changes Alice's status too. But what entanglement means for quantum particles is a lot stranger than this. Here's why. Imagine the particles are electrons, which have a quantum property called spin that makes them act like little magnets. If we measure this spin for an electron, we'll always find it pointing in just one direction, or the opposite, up or down, say. Now we can imagine entangling two electrons so that their spins are always pointing in opposite directions. If electron 1 has a spin up, electron 2 must have a spin down, and vice versa. The two spins are said to be correlated. They are like a pair of gloves. If one is right-handed, the other must be left-handed. So now let's say we entangle the two electrons in this way and fire them in opposite directions. We don't know which of the pair is up and which one is down until we make a measurement. If we find that electron 1 is spin up, we know the spin of electron 2 must be down. This is not remarkable because we could do the same thing with the gloves. We could put one in a package and send it to Alice, and the other to Bob. The moment Alice opens her package and finds the right-hand glove, she knows Bob must have the left-hand glove. The handedness of the gloves, like the spins of the electrons, is correlated. But there's a crucial difference in this analogy. The handedness of the gloves in the package was the same from the start. It never changed. It was always the right-hand glove that got sent to Alice. If someone had intercepted the parcel before Alice got it, that person would have seen that it was the right-handed glove. With entangled particles, that's not the case. Remember, all we did at the outset was ensure that the entanglement made them correlated so that their spins point in opposite directions. We didn't specify whether the spin-up electron is number 1 or number 2. You might think, well, okay, it's obviously one or the other. It's just that we didn't know which was which until we measured one of them. Well, that's not quite the case. Say we set up an electron so that it could have either spin up or spin down when we measure it. That's called a superposition. Then the electron's spin orientation simply isn't described until the measurement is made. It's not just that we don't know it yet. There is no definite answer, one way or the other. How do we know that superposition is real and not just an illusion due to our ignorance? One experimental clue comes from a double-slit experiment. This experiment shows that a particle is indeed spread out, like a wave that can be in many locations prior to measurement. But after measurement, the particle becomes distinct and localized. This phenomenon is weird enough just for a single particle, but with entangled particles, it's even weirder because it then seems that a measurement on one particle determines the outcome not just for that particle, but for both of them. When we only measured electron 1, the measurement not only forced the universe to choose between spin up and spin down for that particle, it forced the opposite choice for electron 2 because of their correlation. Albert Einstein thought up an experiment like this in 1935 in collaboration with two younger scientists, Boris Podolsky and Nathan Rosen. They are referred to as EPR for short by combining the first letters of their last names. They didn't do this to show how weird quantum mechanics is, they did it to show that quantum mechanics could be incomplete. In this experiment, it looks as though by making a measurement on particle 1, we're triggering some effect that influences the spin of particle 2. And according to quantum mechanics, this happens instantaneously. It takes no time for the effect to be felt by the other particle. But that's impossible because Einstein's theory of special relativity devised 20 years earlier said that no influence can be transmitted faster than the speed of light. It was as if, as Einstein said, there was some impossible spooky action at a distance that passed instantly between particle 1 and particle 2. Because of this, EPR reasoned that the whole idea of properties of quantum objects remaining undetermined until one measures them didn't make sense. They figured that there must be something, what Einstein called hidden variables, that fixes the orientations of the spins all along, and that we couldn't actually measure these variables to find out the orientations of the spins. That's why they are hidden, but they must exist according to EPR. So the phenomenon that they had discovered, which became known as entanglement, seemed to blow a hole in the logic of quantum mechanics. But others, like Danish physicist Niels Bohr, said that Einstein was just wrong. Bohr said there were no hidden variables, and the fact that entanglements seemed to create these weird correlations between particles was just something we had to accept as reality. There was no obvious way to tell who was right. Scientists remained divided. It was no good just doing the experiment that EPR had proposed because simply measuring the spins wouldn't tell you if those spins had been fixed all along, as EPR thought, or whether they snapped into place after measurement, as Bohr thought. It wasn't until almost 30 years later, in 1964, that Irish physicist John Bell figured out how to set up a clever experiment to determine who was right. It involved running the experiment again and again on pairs of entangled particles, while the experimenters themselves, Alice and Bob, changed exactly how they made those measurements each time. Then you look at how strong the correlation is between the outcomes of measurements as those changes are being made. Bell proved that quantum mechanics predicted stronger statistical correlations in the outcomes of these measurements than any hidden variable theory possibly could. I made a video about how Bell's inequality works if you want to learn more about this. Suffice it to say that when Bell's experiment was first done in a lab in the 1970s by physicists John Clauser and Stuart Friedman at the University of California, Berkeley, it showed that there was no sign of hidden variables, and that indeed outcomes are determined only by the act of measurement itself. And in the ensuing years, this aspect of quantum mechanics has been proven to be correct over and over again. Bohr was right, and EPR were wrong. Now, you might be thinking, how exactly do you entangle two quantum objects to begin with? The simplest way to make these is to entangle them from birth. Like twins, you could say. Typically, researchers make the pair of photons in a single quantum jump. For example, when an atom that has been given some extra energy sheds it by emitting 2 photons at once. There are clever ways of doing this with lasers, which is how Friedman and Closser did it. But there are other ways of creating entanglement between objects like atoms or electrons. The simplest way is to simply bring the particles together and let them interact. If you arrange for one particle to affect the final state of the second particle, then when you put the first particle in a quantum superposition, the pair of particles can end up in a joint superposition, an entangled pair. That's really what entanglement is, quantum superposition of more than one object. So do Bell tests mean that Einstein's spooky action at a distance is real? You might hear that claim, but it's not right. EPR were thinking about entanglement in the wrong way. That's not surprising because what they were assuming was just common sense. So much so that they didn't even know that it was an assumption. They were thinking of the 2 particles as separate objects. And why wouldn't they? After all, they are sent flying in opposite directions in space. And in principle, you can wait until they are many light years apart before measuring them. But once objects are entangled, they're not separate. They are, in a sense, 2 parts of a single object. Here's what that means. In quantum mechanics, objects are described by wave functions. These are mathematical expressions that encapsulate all that can be said about the object. This wave function can be spread out in space. This is why particles can act as if they are waves. Yet, if we entangle 2 particles, they're then described by a single wave function. And since 2 entangled objects are being described by the same wave function, they're mathematically speaking the same object. That's really what entanglement means. And it's why the particle's properties are then interdependent. If you do something to one of the particles, such as measure it, you change the wave function, and so you alter the other particle too, since it is also described by the same wave function. Now, the question you might ask is, how can 2 initially separate particles, by interacting, somehow combine their 2 wave functions into one? It really comes down to the math. Before the particles interact, we can separate the wave functions of the whole system of both particles into a part that describes particle 1 and a part that describes particle 2. But after they've interacted, that's no longer true. We can't point to any part of the total wave function and say, that bit is particle 1 and the other bit is particle 2. This mixing up happens for almost any kind of interaction between them. So once 2 particles are entangled, we can't say anything about one of them without considering the whole wave function. It is as if their properties are now spread out over both. This is why it doesn't matter how far apart entangled particles are located. They're still interwoven by their joint wave function. That's the really strange thing. We are used to properties of an object being in or on that object. If my t-shirt is blue, the blueness is on the t-shirt. It's localized there. If I have a coffee mug that's blue, that's the coffee mug's blueness, not the t-shirt's. But for entangled quantum objects, the properties can be non-local, spread between both objects. Some of the t-shirt's blueness can be in the coffee mugs and vice versa. This brings us to why entanglement is at the heart of quantum mechanics, because what it tells us is that the quantum world has a feature called non-locality. Things at one place don't depend just on what happens in the neighborhood of that place, as they do in the classical world. There seems to be an instantaneous connection between different regions and particles, regardless of how far apart they are. Why isn't there spooky action at a distance then? That's because Einstein's picture was something at one place somehow transmitting its effects to another place, faster than light. The quantum non-locality is an alternative to that picture. What it really says is that we can't think of those 2 places as being distinct. Quantum mechanics collapses them into a single thing. In this sense, quantum mechanics seems to make nonsense of our normal sense of space. In fact, some researchers suspect that quantum entanglement is more fundamental than space itself, and that our notion of space actually emerges from the quantum entanglements that connect objects in a vast web of interaction. What about using quantum entanglement for communication? It's tempting to imagine that entanglement will let us communicate faster than light. Let's say we make a pair of entangled particles and separate them by thousands of miles, so that Alice has particle 1 in China and Bob has particle 2 in the US. If Bob takes a measurement in the US, doesn't that mean Alice's particle in China is instantly affected? Well, yes, it seems so, but when Alice measures her particle, it will seem like a random collapse to her. There's nothing meaningful about a measurement that Alice makes until she finds out how much it correlates with what Bob measured. And the only way to do that is by exchanging information about their measurements, by sending an ordinary message. Email, snail mail, carrier pigeon, however they choose to do it, they'll never do it faster than light. This is why it's impossible to use the correlation between entangled particles to send any information instantaneously. Now, there is at least one advantage to using entangled particles to send messages. You can encrypt the message in a way that it can never be intercepted and decrypted without that description being detected. And they'll know that their message wasn't secure. That's why quantum entangled photons sent along optical fibers or by satellite signals are now being used to encrypt sensitive messages such as financial data in a tamper-proof quantum internet that's still under construction. Entanglement is also key to quantum computing. Quantum computers with just a few dozen entangled quantum bits have been shown to do calculations in seconds that would take conventional supercomputers centuries. It's probably going to play a big role in our lives. If you want to learn more about this fascinating world of quantum computing, there's a great course on Brilliant, today's sponsor, called Quantum Computing. It's a hands-on, interactive course consisting of 33 short lessons that walk you all the way from some of the basic fundamentals, such as the nature of computation and quantum bits, to building entangled quantum circuits, to advanced concepts such as actually creating quantum algorithms using the programming language.
Thank you. I think now probably you would have understood the application of quantum entanglement, we call it as quantum teleportation. Bob ಮತ್ತೆ ಚೈನಾ ತೋರಿಸಿದ್ರಲ್ಲ, that is the application. Actually I had a diagram. ಅವ್ರು ಏನು ಮಾಡಲ್ಲ, ಎರಡು ಕ್ವಾಂಟಮ್ ಸ್ಟೇಟ್ನ ಟ್ರಾನ್ಸ್ಫರ್ ಮಾಡ್ತಾರೆ, ಎಂಟ್ಯಾಂಗಲ್ಡ್ ಪೇರ್ ಒಂದು ಕಡೆ ಇಟ್ಕೋತಾರೆ, ರಿಸೀವರ್ಗೆ ಇನ್ನೊಂದು ಕಳಿಸ್ತಾರೆ. ನಾನೇ ಬಾಬ್ ಅಂತ ಇಟ್ಕೊಳ್ಳಿ, ಕಳಿಸ್ತಾ ಇರೋನು, ನಾನೇನು ಮಾಡ್ತೀನಿ, ಇನ್ನೊಂದು ಎಂಟ್ಯಾಂಗಲ್ಡ್ ಫೋಲ್ಡರ್ ಜೊತೆ ಕಂಬೈನ್ ಮಾಡ್ತೀನಿ. ಕಂಬೈನ್ ಮಾಡಿ ಆ ಇನ್ಫಾರ್ಮೇಷನ್ನ ಅವ್ರಿಗೆ ಕಳಿಸ್ತೀನಿ, ಮೇಲ್ ಕಳಿಸ್ತೀನಿ. ಮೇಲ್ ರಿಸೀವ್ ಮಾಡಿದ್ಮೇಲೆ ಗೆಸ್ ಮಾಡ್ಕೊಂಡ್ಬಿಟ್ಟು ಪಾಸಿಬಲ್ ಕಾಂಬಿ ಯಾವ ಕ್ವಾಂಟಮ್ ಗೇಟ್ ಅಪ್ಲೈ ಮಾಡಬೇಕು ಅಂತ ಅಪ್ಲೈ ಮಾಡಿ ಐ ಗೆಟ್ ಬ್ಯಾಕ್ ಮೈ ಒರಿಜಿನಲ್ ಇನ್ಫಾರ್ಮೇಷನ್. ದಟ್ಸ್ ಆಲ್. Actual information transfer ಮಾಡಲ್ಲ. Thank you. If you have got any specific questions, you can ask.
Thank you, sir. It was very nice session. Myself, Ansuya, I would like to ask whether the quantum computing algorithm can be... One second. Quantum computing algorithms, as you have mentioned, algorithm stage, there is no implementation. So, whether generative AI is going to solve that problem, that is my... Yes, sir. Okay. Yeah, thank you.
It may be using internally. I have not seen the details. Generative AI, whether it is using, I have to see. Maybe you have given a foot for me. I will go through and I will learn whether generative using your quantum algorithm. I will try to find out and see, update my knowledge. Okay.
At the point of entanglement, how the information from spin orientation changing up and down, how it happens at that microsecond or nanosecond, that if you are able to trap.
Sir, first of all, two electrons to interact. I have told some 8 methods, and I can make two electrons to interact, either by photon, impinge a photon, excite it and make that spin direction correlated. So once it is correlated, it will be correlated forever. No, it is not. It's not. That's what I said initially. Don't think that it is what I used the word in the beginning itself. I told that it's not a science fiction. I used the word. Don't think that entanglement is a science fiction. It is reality. I have not told quantum communication where China already done quantum satellite called Jinwan. ಅವ್ರು ಏನು ಮಾಡಿದ್ದಾರೆ ಅಂತ ಹೇಳಿದ್ರೆ, ಚೈನಾ ಬೀಜಿಂಗ್ ಯೂನಿವರ್ಸಿಟಿಯಿಂದ ಒಂದು ಇಮೇಜ್ನ ಕಳಿಸಿ 1500 ಕಿಲೋಮೀಟರ್ ಸೌತ್ ಆಫ್ರಿಕಾ ಇರ್ತಕ್ಕಂಥ ಟಾಪಲ್ಲಿ ದೇ ಹ್ಯಾವ್ ಪ್ರೂವ್ಡ್ ದ ಕಾನ್ಸೆಪ್ಟ್ ಫಾರ್ 3000 miles. Whatever I told, it's proven. Only thing is, what is finally expected is what is called the quantum internet. Okay. Quantum internet ಮಾಡಬೇಕು ಅಂದ್ರೆ you need quantum networks. Now this information is quite delicate. You need quantum repeaters, quantum relays. Entangles, we use a concept called what is called entanglement swapping or entanglement purification across the networks. So other like quantum repeaters are still in the development stage because you have to maintain very, very low temperatures across the repeaters. That is number one. Second one is the technology what is required or the detectors, whatever photonic detectors are too expensive as on today. So research is going on. So what is finally required is the quantum computer sitting in some part of the world. You need a quantum repeater. You need a quantum entangled starting repeating station, quantum relays. So all of them are going under parallel research. So actually in India, the government India has made what is called NQM. It is called National Quantum Mission. There are 4 verticals. One, the 4 technology hubs have been developed in India. One is called Quantum Computing Lab. Other one is Quantum Communication. Third one is Quantum Metrology. Other one is Quantum Sensing. So IISc, they are developing Professor Chandrasekhar. Probably if you have an opportunity, please visit IISc. There is a photonic lab. They have developed 8-bit quantum photonic processor. And there are many, I heard to one of the lectures of Professor Chandrasekhar, lot of military applications they have given, which I am not able to tell outside. He has told 1 qubit what kind of application, 1 qubit application, 2 qubit, even electron voting CBL, voting systems, 1 qubit photonic system he has given. He gave many examples, but I was not able to recall. If you have got an opportunity, kindly visit IISc Photonic Lab. There they have developed. And second one is in Bangalore, you have RRI, Raman Research Institute. There is a quantum lab and professor. They are doing quantum key distribution. And you have got quantum pi index, no? QPI index. They have developed their...
Thank you, sir, for that enlightening and inspiring address. Your insights have truly added a great value to this occasion. With this, we formally inaugurate Ignite AI 2026 and look forward to an exciting week filled with learning, innovation, and collaboration. Thank you all for being a part of this inspiring journey. Wishing everyone a wonderful and insightful week ahead. Thank you, everyone. Thank you.